So, thank you for your kind introduction. Ladies and gentlemen, it's my first time in Dubai. I'm very pleased to be able to present at this conference. Yes, today I will report on, the title changed a little bit, on the sustainability potential of rubber modified bitumen asphalt. I will show you results from the laboratory as well as practical examples. But first of all, when I speak about sustainability, what does it mean? Especially in road construction. So, if something is sustainable, it's durable, it's long-lasting, environmentally friendly, or simply reasonable. The main goals in asphalt road construction are divided in environmental goals, economical goals, and technical goals. So in order to achieve these goals, the amount of recycling asphalt must be increased, the CO2 emissions reduced, and existing resources generally protected. To achieve the economical goals, costs must be reduced and service life extended. In order to implement all of this, we are dependent on innovations and new technologies. So in Germany, the technical conditions. In Germany, the technical conditions of standard bitumen and polymerasfalt bitumen for the construction of road pavement, short the TL bitumen STB, that's the German includes the requirements of standard bitumen and polymer modified bitumen. Here we distinguish between elastomers like SBS and plastomers like PE or PP. But in Germany, mainly SBS is used for the modification of bitumen. So the question is, why do we need better bitumen and a different modification? The reasons are higher traffic and exloads, especially in Germany. More and more exloads. Climate changes. It becomes hotter and hotter, especially in cities. The surface becomes hotter, the asphalt and the bitumen becomes softer. That's a problem, and our roads have a short life and high maintenance costs. So we have to develop new types of asphalt. For example, with a higher deformation resistance. And a big point is a change of chemical and physical properties of standard bitumen. From our side, standard bitumen continuously falls off in quality. That's a big problem. So we need a new way to modify bitumen and asphalt. One possible solution can be rubber modification. So let us talk about the definition. Typically, rubber products in powder form for bitumen modification are produced from recycled tires. According to the definition of rubber modified bitumen and asphalt and the technical guidelines in Germany, the rubber powder must be additivated before use. So in Germany, when we speak about rubber modification, we always mean bitumen with additivated rubber powder or granules. So we can see a good example of an additivated rubber modified granulate here. So the big question is, why do we need a special additivation for rubber in the mix? So when we take crumb rubber or powder without additives, it will act like a filler in the dry process. Dry process I will explain later. And there is no relevant bitumen modification at all. That's the problem. It lays there down. So, for this purpose, Lega has developed a completely new and innovative technology to produce an additivated rubber modified granulate, in short RMG. This special technology acts as a cross-linker between the rubber granulate and the bitumen, acting as a dispersant to form a homogeneous blend that is crucial for effective asphalt and bitumen modification. Some backgrounds. The company Area invests in cooperation with SIS, Lega Recycling, Evonik, and engineering company PTL, that's my company, to prove these things, to test these things out, invest in this product. Oh, Lega comes a little bit later. SIS, some information, SIS has been appointed as an official representative of Lega in the Middle East region for business operations. An area has signed a license agreement with SIS, invested in building a complete production facility, manufacturing this latest technology, bitumen modifier, and marketed across MENA region, South Africa, and India. That's the background information. And the last area slide, SIS and Area have mutually decided and signed an agreement to market the product under Area 5 trademark. That's where you can get this product. So, back to the topic. Why rubber modification? And why better using granules? That's a big point. We see that rubber is the alternative to modified bitumen asphalt. We have a limited availability of other common polymers like SBS. We have a much lower fluctuation in prices compared to standard polymers. And we can save natural resources and CO2 because it's a sustainable product. We can use it in the wet and the dry process. And the main point, I don't list all of the points, the main point is we have improved properties of bitumen asphalt. So let's take a look at the plasticity range of a standard bitumen. The durability of a bitumen is limited by the plasticity range. In the high temperature range, for example by the softening polymer ball and the DSR, complex granules. In the low temperature range, by the breaking point or BBR, or the stiffness of the bitumen. If these limits are exceeded, the risk of deformation in summer and cracking in winter are increased. So the use of SBS generally has a positive effect on the high temperature range, but there is little or no effect on the low temperature range. So at last, the rubber modification has a significantly greater positive effect on the higher temperature range and at the same time also improves the low temperature behavior of the bitumen. So the dry process allows a much higher rubber content. We can put more and more rubber. So we can further optimize the deformation behavior of the bitumen. So aging is a big problem. The next figure summarized the results of the aging tests in a bar chart. The aging rates are compared between a bitumen 50-70. It's point. Is this one? A PLB with SBS. This one. SBS rate about 3%. And 3 rubber modified bitumen. One with 8 additivated rubber, 10% additivated rubber, and 12% additivated rubber. Each in relation to the unedged test specimen, the increase of stiffness after aging is presented. So we can see, it's here, the gray one is the original, the fresh bitumen. The blue one is after the short-term aging, rolling thin film Often test, and the green one after pressure aging vessel, or the long-term aging. So we are looking at the factors. Here it becomes obvious that the standard bitumen is aged by the factor 12.8 and the PUB by the factor 12.3. The same. In contrast, the 5070 with 8% activated rubber is just aged by the factor 5.5, also half. So the aging rate is significantly lower with rubber modified bitumen to PMBA and the corresponding basic bitumen or standard bitumen. Furthermore, there's a trend that the thermal oxidative aging decreases with increasing degree of modification. You can put more rubber in it, and the aging factor, you can see this, goes from 5.5 to 3.0. It's a significantly better aging rate. In order to show that rubber modification also works with bitumen for this region, comparative tests were carried out. One objective was to meet the requirements to type B rubber modified bitumen according to the Indian standard. In this case, a 6070 bitumen from area was tested first. This was compared with the PMB according to the German guidelines, the German PMB, about SBS content 3%, I think. Finally, areas 6070 was modified with 10, 12 plus 5 and 15% of the rubber modified granular. So a large number of tests were performed. You can see the small thing, it's okay. But in summary, it was shown that all three rubber modified variants pass the requirements. Furthermore, it has been shown that the high temperature range, the rubber modified bitumen with RMG shows significant better results than the PMB. So let's take a look at the results of the high temperature in detail. So the left diagram shows the softening point ring ball, and the right diagram, this one for the complex shell rings. Both diagrams show the 6070, it's the red one, it's the blue one. The PUB, it's the red one. And the light gray with 10%, middle gray with 12.5, and the dark gray one with 15% RNG. So you can clearly see in the high temperature rates, the rubber modified bitumen shows significant better results in the standard bitumen and the bitumen with SBS. You can see we came from 12.4 degrees C, it goes up to 16.6 and 20.4. So with an amount of only 10% of activated modified rubber, one can reach an even higher softening point and complex modulus than the SBS modified bitumen. You can see here it's comparable 61.8 to 63.6, and this is significantly the complex shellness, the stiffness of the bitumen at 70 degrees C goes up to 200%. So with higher rubber contents, these characteristic values can be increased even more significantly. Summary of the bitumen test. In summary, you can achieve obvious higher stiffness by rubber modification in the high temperature area. That means less cracking, less deformation. In the low temperature area, we also have key advantages over the PUB because of the lower stiffness. And we have a better aging behavior and UV resistance. So this is extremely helpful in countries with large temperature fluctuations or extreme temperatures. We have advantages to both sides. In German technical guidelines, we differ between the wet and the dry process. I talked about this before. So in the wet process, the rubber is blended with bitumen. The resulting bitumen should be used like a ready-to-use bitumen. The wet process is used, a big point, is used to produce rubber modified bitumen. The dry process, in the dry process, the additivated rubber or granulate is dosed directly into the asphalt mixing unit during asphalt production. So the dry process is used to produce rubber modified asphalt, not bitumen, but asphalt. We are modifying our whole asphalt. So what are the advantages? A great advantage is that the dry process is possible at all asphalt mixing plants. It's no problem. Due to the free choice of the base bitumen and the variable control of addition quantity, customized solutions can be supplied for almost any application. So, in regions with very low temperature, like Dubai, we can use a softer base bitumen with rubber. And for regions with high temperature and high loads, we can use a harder base bitumen with rubber or with more rubber. So another advantage is a variable addition when using red. With higher red content, we have generally problems with ready-to-use PMBs. We need to increase flexibility in polymer modification due to the increasing processing of reclaimed asphalt in asphalt surface and asphalt vinyl mixes. I'll give you an example. A bitumen, it's a PMB in Germany, 25, 50, 50, 50, 50A, contains, I've mentioned it before, 3% SBS. In the mix, it's okay. But now we put some red in it, 30% red. We have only 2.0 polymers in the whole mix. So in Germany we don't use 30, but often 50% red. So we have only 1.5 polymers in the mix. So in the base layers, 70% red, no problem. We have only 1% polymer in the mix. So we want 3, we get 1. That's the problem. Oh. With rubber modification, you have completely variable addition and no problems modifying asphalt mixtures with high wet content. You can put them into the mixing unit. No pumps, no high viscosity, no problems with pumping this from this to this. It's all okay. One great advantage of this rubber modified granulate is that this technology gives a real 3D modification of the whole asphalt mixture. The computer tomography images, you can see the rows, show a uniform distribution of the additivated rubber particles in the produced asphalt. For example, it's an SMA 11. You can see this is the rubber. It's in the whole asphalt. So I speak about practical examples. That's the first one. The example shows the long-term study of an SMA with 50% red. It's a dead Moiler street in the city of Paderborn in Germany. The street had to be renewed in 2012. The aim was to use as much red as possible from the road for the new asphalt surface. So the laboratory test had shown that the bitumen, the old asphalt, was already very aged and the polymers in the bitumen were no longer active. To solve this problem, the new SMA was produced using 50% red with a softer bitumen, 70-100 with a content of 15% additivated rubber. So we make a monitoring after 10 years from 2011 to 2022, it shows no deformations and no cracks. After 6 years, the laboratory results shows low aging, a very high elastic behavior, and very good stability against deformations. So the second example is about additive rubber modified asphalt under high static and extreme dynamic load. At the Lega port side in Moscow, cranes in the weight range of 400 to 800 tons are stored and moved very slowly at 3 kilometers per hour. Very slow. It's not good for the asphalt. Very, very slow. No? And in addition, the very large asphalt surface become up to 60 degrees C hot in summer. The production of the rubber modified bitumen asphalt took place in the year 2007. After 13 years, under the high stress, very high dynamic and static loads and high temperatures, the asphalt surface is basically in a very good condition. The results from the laboratory shows very good low temperature and good aging behavior. The results for the deformation in the high temperature range also very, very positive. So the further use of the area is not restricted in the next years. This example also shows rubber modified asphalt after 11 years under high static and dynamic loads. So there are no significant substantial damage in the area. You can see this here. So comparable with the results before, we have very good heat and cold properties for bitumen and asphalt. Low aging of the rubber modified bitumen and confirmed effectiveness of the elastomers. So in this last example, 3 different sections of a road were renewed. The different layers were produced with standard bitumen, as variant 1, with P&B, variant 2, and with additivated rubber. This means for the surface layer 50-70 with 12.5% additivated rubber and so on for the other layers. So a lot of asphalt values were determined by laboratory tests, really a lot of, with the results from the laboratory comparative computational dimensioning calculations were made in Germany. We have the RDO, that's the norm for computational dimensioning, or the standard for this dimensioning calculations. So as a result, up to 23% more surface life was calculated when using additivated rubber instead of FBS in the different mixes. So the last diagram shows the stiffness of asphalt as a function of temperature. In this diagram, 3 variants of the binder layer are presented. One with a standard P&B, one with a standard 2, sorry. It's a black line, one with a P&B, it's a blue line, and one rubber modified, it's a green line. So you can clearly see that in the range of the high temperature range, the rubber modification leads to the highest stiffness. So less risk of cracking or other deformations. In the low temperature range, the rubber modified asphalt has the lowest stiffness and the best crack resistance. So in this case, the additive rubber modified asphalt has near perfect performance. Good in summer, good in winter. So finally, the conclusions. The results have shown that the rubber modification is technically superior. Less deformation in summer, high elastic properties, reduced cracking in winter, and high aging resistance. The laboratory results and the practical examples indicate a much longer service life, not live life. We have a big advantage with the dry method and with rubber modified granulate. With this new technology, a real 3D modification of the whole asphalt mixture is given. We have flexible dosing rates. The product can be supplied as needed, applicable to all bitumen grades. And finally, an additional energy saving potential because we need no special or complex construction such as a colloid mill for the incorporation of SPS. Thank you for your attention.
Thank you so much, Dr. Govilan. But before you leave the stage, I would request the Asphalt team to join us on the stage for a